Test 1, 2. Môre. Is dit Liesel aan die ander kant? Liesel, are you there? Or your microphone is not, the volume of the microphone is not on or raised to its max. So I can see your microphone is activated, but it's not transmitting. So the mic volume is either off or not high enough. Hy sal nou deurkom.
Waar kyk mens vir die
Ek weet nie regtig, ek het 'n eksterne mikrofoon wat ek inplug en hy tel dit net op outomaties. Maar jy het so 'n Windows knoppie aan die onderkant regs, of jy kan net by jou search fasiliteit microphone intik en dan sal hy vir jou sê watter mikrofoon hy gebruik. Jy het obviously 'n laptop met 'n built-in mic het, wat net nie aangesit is of weer is nie. Praat gou met my Liesel en kyk of jy jou kan hoor.
Kyk gou, ek soek nog vir
Ek hoor jou. Dis net
nie my hoor.
Ja, ek hoor jou, maar dis net baie aan en af. Het jy dalk internetprobleme aan julle kant?
Want ek het fiber met 20 meg lines. Is dit nie, dis nie.
Nee, is nie internet nie.
En dan kyk ek op die self om dalk net
Ja, iewers is jou mikrofoon glad nie lekker nie. So iewers klik op jou Windows button en dan tik jy net daai microphone in daaronder. Of sound.
So te kry.
Daar sal sê setup microphone. As jy in jou Windows button aan die onderkant tik microphone, dan gaan hy sê setup microphone en dan gaan hy jou mikrofoon detect. Ek wil nie myne doen nie want dan gaan hy dalk opneek. Of jy gaan net sê sound. En dan gaan hy sê gaan jy net na die sound ding toe, daar behoort jou speakers en jou recording, jou mikrofoon, alles te wees. Weet jy waar die Windows search in die onderkant is?
Ja.
So jy sound. Dan gaan jy tik net sound in. En dan klik jy daarop. En dan gaan jou sound te swak is. Jy gaan sien speakers en dan die playback met ander woorde en die volgende is recording. En daar sal 'n mikrofoon wees en dan sê vir jou watter mikrofoon. Ek het 'n internal microphone en ek het 'n Samsung Meteor. Nou myne is gestel vir my Meteor, maar albei my mikrofone tel my 'n bietjie op. So hierdie Kinetic ene moet afgehaal word eintlik.
Okay, ek is hier op die settings.
Het jy die mikrofoon se settings?
Alles is klaar op 100.
Ek hoor jou, so jou mikrofoon werk, maar hy sny net die hele tyd uit. Ja, wat jy kan ook doen, Liesel, net vir vandag miskien. As jy met 'n selfoon, ek weet nie of jy op julle selfoon ook Zoom kan gebruik nie. Dan slaai net met jou selfoon in, jy sit jou rekenaar se klank af en praat jy deur jou selfoon en kyk deur jou rekenaar. Dis 'n opsie.
Dit probeer gegaan.
Maar dan moet jy net jou rekenaar se mikrofoon afsit, anders gaan jy feedback kry.
Reg, ek sal dit nou afsit.
Ek hoor jy nou weer goed. Ek hoor jy actually baie goed.
Ek of dit nou die sein was.
Okay, hierso sien ek ja. Ek join jou gou op 'n ander device. Okay, en nou?
Hy die rekenaar afsit.
Jou rekenaar se klank is nou baie goed.
Is
Actually.
dit nou goed?
Ja, is goed. Hou albei ingesign. Net so. Okay, ek weet ander leerders ons gaan join vandag nie, want hulle het een of ander Engelse ding aan.
Is reg? Baie dankie dat jy nog steeds ons gehelp het.
Nee, dit is hoe dit werk. Die afgespreekte tyd is die tyd. Ons moet nou net eintlik vandag gesels het. Gehoop almal is hier. Ons moet gesels het oor 'n tyd in die week wat almal pas. Die rede hoekom ons dit Vrydag gedoen het, Liesel, is omdat ek wil nie die organiese chemie aanbied nie. Ek wil hê my suster moet dit aanbied, want sy is 'n Engelse science tutor. En daai benaming en goeders moet ek nou gaan oorleer in Engels.
Ek verstaan dit mooi.
So sy sou sê nou maar 3 lesse gevat het vir julle vir benoeming en as ek julle weer gesien het. Maar dis nie 'n krisis nie. Ek kan dit doen. Ek gee in Engels, maar ek het net so lank klaas daai organiese chemie gedoen en die skryf in Engels is heel anders en mens mag jy 'n foutjie maak nie, so dis baie finietjie.
Ek dink die lesse dalk op 'n Woensdag is, maar dalk daai een wat die suster moet aanbied op 'n Vrydag is dan op ons plan.
Ja. Ons sal iets werk. Ons sal iets uitwerk. Ek gaan net gaan uitvind by hierdie mense of hulle leerders gaan kom.
Is dit reg?
Okay, is it Kakehu? How do you pronounce that name again? Liesel is jou leerder daar.
Siso, hy sê baie skaam. Sy naam is Putso.
Sorry, ek kan nie hoor nie. Ek kan glad nie hoor nie. Sit gou jou selfoon se klank aan. Aktiveer gou jou selfoon se mikrofoon. Daar's iewers wat jy moet select daarvoor. Okay. Ek gaan gou jou mic mute van jou rekenaar en dan sit jy jou mic het nou geaktiveer op jou selfoon. Jy moet hom net aansit. Ek kan jou seker unmute ook hierdie kant. Ask to unmute. Ek kan nie unmute, ek moet jou vra om te unmute. Ek dink jy het jou rekenaar se klank aan nou weer, Liesel, is dit?
Ja, my selfoon se klank afgesit. Die rekenaar se klank is ons oor die foon.
Is jy nou oor die foon?
Ja.
Ek dink jy is oor jou foon nie.
Die klank van die rekenaar af.
Liesel,
Okay, ek gaan die klank net by die rekenaar afsit. Allee, hoor jy my?
1000 keer beter.
Alright, ek het hierso nou harder gesit. Can you hear him?
Welcome to the class, Reese. Can you hear me, Reese? Reese?
Hello.
Where's your friend?
They're here.
Okay. They must be logged in 5 minutes before the class starts.
Yes, sorry.
to sort out all your microphone issues and
Okay.
okay. This is how my classes work. I start in 4 seconds. If anyone misses something, that's his problem. I can't be having people logging in at 11:30. You must all be logged in at 11:25. So we can just say hi. Otherwise, I'm wasting some of your tutoring time to speak to you, to ask you how you're doing, just to remind you to send more examples, etc. We only have an hour, so we must make the most of it. Right, I'm starting. I'm just going to run through all the equations again that we did last week, just to make sure that you are actually using them correctly. Okay, your friends are not going to log in today, is that right? Please, don't worry about them. We'll continue. Okay. The first equation is just your normal momentum equation. Momentum equals mass times volume. Not volume, velocity. And that velocity is in meters per second, and the mass is in kilograms. So you have a unit, kilograms meter per second. You're not allowed to use any other units. I've never ever seen a paper that allows you to answer that in any other units, except you're also allowed to use Newton seconds, which is exactly the same. Okay, cool. Then we have change in momentum. Change in momentum, basically delta P. Change in momentum is just basically the mass of the object times its change in velocity. So you have a final velocity minus the initial velocity. And then we can also work out the force exerted on that ball or whatever object. And the force, it's the net force or resultant force times the change in time, or the time that that object is in contact with another object. If the ball bounces on the floor, that delta T is the time the ball is in contact. Very important. It's extremely important. It's not the time that the ball, so if I take a ball and I drop it from the roof of the house, it takes 2 seconds to hit the ground, but it stays in contact with the ground at 0.1 seconds. Now that time, it's got nothing to do with the time it takes for the ball to hit the ground. Nothing. It's just the contact time or impulse time. Very important. This chapter is gonna integrate with another chapter, and then you can get confused if you're not with it. And that equals the impulse or the change in momentum. All right, so what I'm going to do, I'm just going to run through examples that you've posted. And afterwards, there should be time, and then on the left, and then I'm going to start the new part of the chapter. Okay, this we've done. Okay, learners' questions. That was the first one submitted to me. So we just do it in the order. Okay, they're giving you a graph. Let's just zoom in on this graph, basically. So I'm going to draw a little picture of what happens here. I have a ball. So for instance, during a hockey game, okay, the ball is on the floor. During a hockey game, Nadia hits a stationary ball of 200 grams. Okay? And this graph will give you the force against time. So in other words, the graph is just going to be illustrate or be a graphical example of the time that the object, like a hockey stick, is in contact with the ball. So just that contact time. Now, if you look at the x-axis, you'll find that the contact time is 0.0 seconds. That is the time that the hockey stick is in contact with the ball. Now, what happens? I wish I could show you slow motion, but the minute or the millisecond rather that the bat hits the ball, the force actually starts at 0. And then it increases as the ball squashes in. I don't know if you've seen this, but if I have a big stick here and there's a cricket ball coming and that ball hits the stick, I'm going to show it from the side now. This is the side of the stick. The ball doesn't look like that on the stick. Right at contact, it does look like that, but the ball actually squeezes in and becomes flat. So if this is a stick again, the ball flattens, the ball squashes in. And that time that it squashes in and goes out again is this 0.0 seconds, 0.06 seconds. So the force increases up to 100 newtons, and then as the ball leaves the bat again, it decreases to 0. So now, very important, I'm just going to take this away, delete this. Very important. They say use the graph to determine the impulse of the ball. Now the impulse is change P. That is impulse. Okay, I'm not allowed to do a calculation from the equation. I have to use the graph. But say for instance, I did the calculation from the equation, I would have used this calculation. F delta T is delta P. So this is what they want. So I need to just take the average force or the resultant force and multiply it by the time. But now the force isn't constant. The force goes from 0 to 100, and then from 100 to 0 again. So the average force on each of these axes is basically 50. So if I wanted to use F delta T is delta P, which I'm not allowed to because they are forcing me to use the graph. I'll show you now how to use the graph. I'll just say 50 newtons average at 0.06 is the change in momentum. Just put that in a calculator, everyone. That's 3.
Yes, it's 3.
Okay, so the change in momentum is C what? You can write Newton seconds. They're not giving me a direction. So I don't know which direction this ball is going. But that's not the point. Okay, but you're not allowed to do this anymore. You must use the graph. Now the area under the graph equals the change in momentum. So let's work out that area of that whole triangle. So change P equals what? The half base times height, because it's a big triangle. Half, the base is 0.06. And the height is 100. And that will give me what? P, Newton seconds. Or you're allowed to use kilograms meters per second. But normally they use Newton seconds if they use the F formula. That easy? Yes, but if you didn't know that you need to use the area under the graph, then you would not have be able to do it. Okay, so this will give you 0 marks, although on the top will give you 0, so no marks, because you've not used the graph, you've used the equation. You're not allowed to use the equation if they say use graph. Right, cool. Next question. Okay. Right. I'm just going to try and make this bigger so everyone can read. There's a car and it's got a mass of 1,200 kgs. It's traveling at 72 kilometers per hour. Oh, big problem. 72 kilometers per hour. Why? The unit is wrong. Let's convert that unit to meters per second. Do you know what to do? Does anyone know how to do what to do? Converting from kilometers per hour to meters per second. You divide by 3,6. I can explain that, but let's see how much time we have. The best is just to learn. It's a 3,6 ratio. So if you go from kilometers per hour to meters per second, you divide by 3.6. Okay, so do that. 72 divided by 3.6. Easy. 20. 72 divided by 36 is 2. I just add a 0 to compensate for that. That's 20 meters per second. You're not allowed to use kilometers per hour. Okay, so when the driver sees a dog running across the street, he brakes, and 10 seconds later, So then 10 seconds is the time for the impulse to occur. So that's delta t. And then its final velocity. So this is his initial velocity. And then its final velocity is 18 kilometers per hour. And you're going to convert that by dividing 18 by 3.6. That's 5. Right. So now I've got the right units and everything. So now they ask you, calculate the initial momentum of the car. Right? The momentum of the car, you can put an I there for initial if you want to, is the mass times its initial velocity. Okay, we're going to just check the sum again if there's any direction given. No. So the mass of the car is 1,200 kg and its velocity is 20. And that's 24000. But kilogram meter per second, because we're not using the force. We're not, if I use force with the calculation, I'm going to use Newton per second or Newton seconds. Okay, and this is, yeah, I'm not going to give you any direction. Not going to bother. Okay, so that's wrong. Why? Some other way you converted the 72 kilometers per hour to 72,000 meters per second. 72,000 meters per second. That's like, I don't know, what's the circumference of the Earth? That's like going around the Earth in 1 second. That is not possible. Okay? Look at this conversion. Very important. Take a screenshot, maybe of this page. I'm also loading this onto YouTube. No? You can look at this lesson again. Next example. Right. The front of, okay, cool. What do I need to explain here? This is something, just help me out here. Is this, do I need to do all the examples here? Or is there something specific I need to explain?
Oh no, it's just from number 2 and on.
Okay, cool. So this is the memo you've posted. I'm just going to get the memo out of the way. Right, let's quickly read. The front of modern cars is intentionally designed to crumble in case of head-on collision. Yeah, so if you crash the car head-on, the whole car squashes in. That's to absorb energy. Remember, the longer the contact time, the lower the change in momentum. Very important. If you can get the car to be involved in an accident over a long period of time, then the impact or the change in momentum on the driver is the least or much less. So they design the cars to crumble up as they crash, so the person inside doesn't experience a huge change in momentum, so it doesn't get injured that quickly. Okay, so there's a guy called, I think, Jaffa or something. He's wearing a safety belt and his car is moving at 20 meters per second west. I'm making a little note there of what's happening. 20 meters per second west. So that's going to be positive. The car crashes into a tree and the front crumbles by 1,55 meters. That's not part of any of the equations. Okay, number 2. Sorry, Reese. I'm just going to mute you. How long does it take for the car to stop if the deceleration is constant? Okay, now we have a small problem. This is not part of your chapter. This has to do with equations of motion that you haven't actually done yet this year. Maybe you've done some of it in grade 10, but you haven't done any equations of motion yet. That's part of the next chapter, but we can quickly look at that. Calculate how long it takes if the deceleration is constant. So we don't know the deceleration, so we don't have the value of A. So you need to find an equation that as initial velocity in, final velocity in, time in. And that is this motion equation. V final plus V initial over 2, I think times delta t is delta x. So that's the equation that, if you didn't know this now, it's fine because you haven't done the chapter yet. So they've slipped in a question here that doesn't belong in the book yet because you haven't done these equations yet. Right, so this final velocity is what? If the car stops, the final velocity is 0. The initial velocity is 20 over 2, and the time it takes to stop, I don't know. Okay, and the delta x is the displacement. It is 1,55 meters. So that the car will displace or move forward at during that collision at 1,55 meters. So you just do that calculation. I don't have to explain this to you. This is 10 delta t equals 1,55. So delta t is 0,155, and we need to use 2 decimals, so 0,16 meters. Do you have a memo somewhere? I just
Yeah, I think it's there.
deleted the memo. Or I moved it somewhere. I don't know where it is. Oh, there it is.
There's it up there.
Okay, they didn't round off to 2 decimals. Doesn't matter. So they just left the answer like that. Right, number 3, calculate the force that the safety belt applies onto Jaffa if he has a mass of 65 kilograms. So his mass is 65 kg. Just tell me, Reese, did you also do these examples in your book?
I haven't yet.
You haven't yet.
I don't think so.
Right. I just want to remind everyone that you are doing physical science. You're doing 1 hour of physical science every day. That is
Okay.
basically the minimum requirement time-wise for you. Otherwise, I don't see you passing it. That's as simple as that. I just want to make sure that everyone understands that if you were at any school in the vicinity, you will be having an hour of physical science classes every day. Every day.
So we're just battling to hear you. Our connection isn't very stable here.
Oh, really? I can actually hear you very well. Can you hear me now?
I did.
Can you hear me, Reese?
We're having problems with the internet.
Okay. Okay, no problem. This is also, like I said, I'm also recording this, so I'm going to send a link so you can re-watch it if you have missed anything. Right, okay, now Jaffa is 65 kgs in weight. Sorry, his mass is 65 kgs. Calculate the force that the safety belt applies onto him. Right, what equation are we going to use? Anyone? Force, delta T is delta P. Okay, right, very important. The force is horizontal. So the force that the belt exerts on him will be backwards, for instance, and the Newton components be the other way. I'm just going to delete this force because it's not applicable for now. Right, so the force times the time that it is in contact with the seat belt, which we've just worked out. So the force times 0,1, no, that's not the time. It is the time. Look at me. I've got a wrong unit here and no one's seen it. That's seconds. Is the change in momentum. Let's work out the change in momentum. What's the change in momentum? Change in momentum is the mass times the final velocity minus the initial velocity. So the force times 0.16 equals Jaffa's mass, 65. His final velocity would be 0. And his initial velocity is 20. Cool. Calculate that quickly. So you all on one PC at the moment. I get -8125. So the force is 8,125 newtons. What? East. Remember, we chose west as our positive move direction right at the beginning because the car was moving west. So now we get a negative force value. So the safety belt, obviously, if you're moving west and you crash, then the safety belt will exert a force on your body in the opposite direction, which will give you a negative value. Okay, number 4, I'm not going to explain again. Explain the importance of the crumple zone. What does the crumpled zone do? Why does they build a car so that it crumbles up? That gives extended contact time, and force is indirectly proportional to time. In other words, the longer you're in contact with two objects are in contact with another, the lower the force. And you're looking for that low force or low impulse or low change of momentum on the driver so that he doesn't get injured. Besides safety belts, what other precautions is used to protect cars? This is just me studying something like an airbag, maybe. Right, next. Okay, this one you can do because we've just done examples similar. What physical quantity is represented by the area of the graph? The area of the graph is giving us the change of momentum. You can't just write there. You must write impulse or change of momentum. 2, sorry. Calculate the change of momentum. The change of momentum is the area under the graph, half base times height, 140. Everyone work out that quickly. That's 7 Newton seconds, or you can use kilogram meters per second. I wonder what the memo did here, which unit they're using. They're using kg, yeah. They were using the following. They will be using kilograms meters per second if there's no F value in the equation, and they will be using newtons per second if there's a F value. They are similar, but let's just follow the book and just say, okay, fine, even though Newton seconds is correct, so similar, we're going to use kilograms meters per second if we're only working out the change in momentum. If the ball hits the ground at 4 meters per second, calculate the speed at which it leaves the ground. Oh, that's quite interesting. I wonder if you can do that one. What is the velocity that it leaves? Okay. What is the most important thing I taught you last week? Do you think? What do you think is the most important thing that I'm teaching you? Or what is the most important thing that you can learn in physics? The most important thing is that you are not solving the problem. I'm not answering that question. I'm not solving it. One of those science equations is solving it. So I'm going to find the equation. Right, so they want to know if the ball hits the ground at 4 meters per second, calculate the speed at which it leaves the ground. So I'm just going to use this equation. The change in momentum, which I've just done, is the mass times the final velocity minus the initial velocity. Now we must be just extremely careful. I'm going to choose downwards as positive. That means the velocity initial. Sorry, you want to say something?
No, that's fine.
Okay, very important. I need to choose a direction. I'm always choosing downwards as far as possible as positive. That means the initial velocity will be positive. But when the ball leaves the ground again, the final velocity will be negative. If downwards is positive, then upwards is a negative value. So in other words, the mass of the ball, which they've given us as 1 kg, the final velocity I want to calculate. Now you can write there negative FV, or you can just write velocity final, but you realize already that you're going to have a negative value. And then minus the initial velocity, which is what? 4 meters per second. And the change in momentum we've just worked out, it was 7 kgs or meters per second. Right. So now what? Look at this. There's a slit problem here. This graph doesn't have any direction in it. So in real life, that should have been a negative value on P. So I need to get a negative value, or you need to just realize that we need to get an upward answer. So this is 7 equals final minus 4. 13 equals velocity final. So I don't need to put the negative in, as long as I'm telling them that it's 13 meters per second upwards. Okay, just give that direction, because velocity is a vector and you need to give direction. Snap that. Just want to see how they have actually done it on the memo. I don't know where that memo is. Is it this one? Okay, I don't have that memo. So why is it 3? We made a mistake. Want to check that? We have it. They have a 3. Okay, obviously. Sorry, I made a mistake here. Look at this. This needs to be a negative 7. The change in momentum is upwards. I did say that, but I didn't never gave a sign. Therefore, negative. So this is negative. So this is negative 3. So the final velocity is 3 meters per second upwards. Right, that 13 we just got, or I just got, is obviously wrong. Why? Think about it. You can't the ball can't hit the ground at 4 meters per second and then leave at 13 meters per second, because then extra energy needed to be added to the ball. So that 13 was just obviously wrong. Okay, do you realize that? If you take a ball and you throw it downwards, or it lands on the ground, and it hits the ground at 4 meters per second, now, it can't leave the ground at more than 4, unless someone has added energy to that ball. So the 13 I got was an obvious wrong answer. Okay, so that change in momentum was negative because it's upwards. They might have positive values on the memo because they might have chosen upwards as positive right from the beginning, and then their values will be just, then they'll have a positive 3 as an answer. We choose negative as upwards or positive as downwards. Yes, I'm listening. Who's chatting with me?
I don't think it's anybody.
Okay. Okay, so Reese, you need to somehow sort out the next time. What you need to do next time is maybe, if you can hear me, just log out and log in again. Okay, we're just going to let them log out. Because we finished with all the questions, I want to start a small new section. I'm going to give them a minute just to log out and log in again. Okay, cool. Okay, so Legal, you're still with me, eh? So can you just spell your name for me, please? Is it Kehu, or how do you pronounce? Just spell it for me if you don't mind.
KHUTSO.
Is that right?
Yeah, I think so. Yeah.
Kutso.
KH. Yeah, Kutso. Yeah.
Kutsu.
Kutso.
Kutso. Okay. Cool. So you saw that I can actually change your name. You can also go and change the name there. Otherwise, I'm just gonna call you Liesel. That's gonna work very well.
I'll change it.
Okay. Right. Let's go. Law of conservation. New chapter. Right. How about now, Reese? Quickly speak to me.
Yes, we can hear.
Wonderful. Okay. Just the following. You need to log in 5 minutes before it starts. You need to, by then, send me on WhatsApp some of the examples you've done that you're struggling with. If you're not struggling with anything, then I'm going to give you a lot of work to do, because then I'm going to give you harder examples because you can do all the ones in the book. Thirdly, also, you need to do all the stuff that we do here. You can't now, anything of the stuff that we've just finished, you can't have anything outstanding. Because if you have something outstanding now, it means you're going to have questions about work that we're not going to be looking at again. So we're starting a new part of the chapter. And basically what you're doing, you haven't done your work, so you're going to just fall behind. Okay. This is the subject you've chosen. Physical science, you've chosen the subject. It's the hardest one of all the subjects in school. And it's the one that's going to take the most from you. So there is just no excuse. You always have all your work done. You've always have questions about the stuff you don't understand. You always prod me and say, well, you're going too fast, or you're always on the ball. That's the term we're going to use. If you're not on the ball, the subject...
I'm sorry, we're having problems hearing you again. I think it's just there's too many devices this side connected.
Okay, but then switch off some of the devices.
We can't. Other students are doing webinars as well.
Oh, okay. Right. What I'm going to do, I'm sending you a link of this recording afterwards. Okay, let's start new chapter. If you don't hear me at all, then you're allowed to log out and just listen to the recording afterwards. Okay, law of conservation of motion. Next part of this chapter. So this whole chapter is about momentum and impulse. We've just done the impulse bit, or the change in momentum bit, and the forces. Now we're going to do a second part called law of conservation of motion. And you have to learn a definition. And your definition is something like this. Use the one in your book. It's the total linear momentum. The total linear momentum of an isolated system remains constant. In other words, if there's no external forces on an object, like friction or air resistance, then that object will not lose any momentum. So, if two objects are, say for instance, moving east. I have a 2 kg block here. It's on wheels and it's moving at 4.5 meters per second east. And there's another trolley or a block on wheels, and it's moving at 3 meters per second east. Now, obviously, the 2 kg one is moving faster, so it will eventually crash into the 7 kg block or trolley, whatever. Once it crashes into one another, then the momentum that the whole system had before the accident will be exactly the same as the momentum after the collision. So no momentum will be lost during that collision. So we use this equation. That funny sign is just called sum. So this says the sum of all the momentum we had. Okay, that was a bit of Afrikaans slipping in there. Voor means before. And the sum of all the momentum now means after. So in other words, all the momentum that the system had before the collision will be exactly the same as all the momentum afterwards. So let's just do the sum. Let's make a question out of it. So let's get this block here and make our own question. So I'm just going to say this is before. And after the collision, I'm going to say that the 2 kg block is in rest. And the 7 kg block is a bit bigger, is moving in that direction. So basically, there was a 7 kg trolley moving at 3 meters per second, and a 2 kilogram trolley was coming from behind, crashing into it. And after the collision, this is the crash here, bang. After the collision, the 2 kg velocity is 0 because it just stood still. Then this 7 kg trolley is continuing moving towards east. The velocity will be higher. Obviously, if something crashes in from behind, your velocity will increase. I want to know what is the velocity of the 7 kg trolley after the collision. And I'm going to show you how to do the sum. So we have the sum of the momentum initial is the sum of the momentum final. You can also use E in before or after, whatever. Just initial and final is fine. So let's just do that. Okay, we have a mass and a velocity of 2 kg. Or you can write it like this. Maybe it looks better. M2V plus M7V. The mass of the 2 kg trolley times its velocity plus the mass of the 7 kg trolley times its velocity. Why? How can I get these equations? Oh, because P is M times V. Momentum is mass times velocity. And that will equal what? The mass of the 2 kg times its velocity afterwards plus the mass of the 7 kg and its velocity afterwards. So what's the mass at the beginning? 2 times 4.5. So in other words, I have chosen as positive plus the 7 kg times its velocity of 3 equals what? Well, the 2 kg is in rest now, so that will be just 0 because it will be 2 times 0, which is 0, plus 7 times v because I don't know the velocity. So this is 30 equals 7v. What is 30 divided by 7? 4.1.
I get 4.29.
Yes, very good. 4.29 meters per second east. It is really not difficult. So the law of conservation of momentum sums is really kind of easy. We're going to do 2 more examples and you're going to ace it then. They are going to make it slightly harder. This is going to integrate with another chapter again, where there's friction and a lot of other stuff. But at the moment, this is a breeze. Okay, cool. Right. I think the picture says it all. We're just going to run through it. I have a 3 kilogram object moving at 4 meters per second to the east. There's a 2 kilogram trolley or object. It's standing still. So in other words, picture yourself. You're in a shopping mall, like say if you're in Pick and Pay, you've got a trolley there, and you've got 3 kilograms of stuff in the trolley. Now there's another trolley standing there in the aisle, just still. And you're gonna push that 3 kilogram trolley you're gonna slam it into the 2 kg. The 2 kg trolley is standing still at the moment. Then, bang, there's a collision. After the collision, the 2 trolleys are stuck into one another. So they've slipped into one another, now they're stuck together, and they're moving in that direction at a velocity we need to calculate. Right. There's a certain way of doing it. You have to write the sum of the momentum initial equals the sum of the momentum final. They're going to tell you a whole story there and also tell you that there's no friction and air friction can also be ignored, blah, blah, blah. But in school, you can't do change in momentum sums if there's friction and stuff in the collision. So you don't have to worry about that. Right, so I have mass times velocity plus mass times velocity. So this is the 3 and this is a 2. Equals, check it out, mass times velocity. Because I have only one single unit there. They stuck. So I have only one unit, one trolley afterwards. Okay, obviously the mass afterwards is 5 kg because they're stuck together. But the velocity we don't know. Initially, we have a 3 kg going at 4 meters per second plus a 2 kg that is stationary. What's the velocity of the system afterwards? Work out V. Is it 2.4 or something?
Yeah, 2.4.
2,4. So therefore the velocity is 2,4 meters per second. What? We don't have direction. You can say in the initial direction of movement, or you can just say to the right. Is that easy? It is. It is quite easy. I want you to try the next example on your own. Let me just get you. This is going to slightly stretch you maybe. There's 2 identical trolleys. I just want to get this forward the right place. There's 2 identical trolleys that are connected with a piece of explosion. There. That green is a piece of explosive. And they're moving to the right at 1,5 meters per second. Then the charge goes off. You've got like a remote in your hand, you push the button. The charge goes off and the one trolley continues to move towards the right at a higher velocity. So this here, blue trolley is this one. And that one just continues moving to the right. The question will be, what's happening to this purple trolley? Because it can be stationary, can also move to the right, or it can move to the left after the explosion. Calculate the velocity of the other trolley. It's going to be the purple one after the explosion. And then they tell you forces due to friction and air resistance can be ignored. They basically have to tell you that so that it remains a closed system. Right. I'm going to help you with one thing. I'm going to give you an equation. Sum of the momentum initial is the sum of the momentum final. What is that?
Sorry.
Oh. You have a bird there. Right, everyone, quickly sit together, take a piece of paper, quickly work this out, set up the sum, see if you can find the value. I'm giving you like 3 minutes, and then I'm going to do it. Take 3 minutes. Make sure that you have the answer that you have will have the right unit. It will have the right, it will have direction in it. And then you're going to tell me if you have it. Right. Are you doing good, so? Still busy?
Almost done.
Reese and friends?
We're still busy.
Okay. I want you, as far as possible, okay, maybe you can't log in each one in his own computer. I'm not sure if you can. One minute. Come, quick.
I'm done.
Right. Reese. Right, let's go. The sum of the momentum initial equals the sum of the momentum final. Right. Initially, there are two objects, they are like joined together. So I have mass times velocity, one object basically, equals mass times velocity plus mass times velocity. I have two objects not connected to one another. So I have two momentum value or sums at second part or afterwards. So this is initial or before, and this is after the collision. So what's the mass before? Well, I don't know. So I'm just calling this one mass M, and this one is M. That one's M, and that one's M. So I'm just keeping it as M. So at the start, I have M plus M, two masses. They're both the same, and their velocity is 1,5. And then that purple one has a mass, which I don't know, and a velocity I don't know. Plus, the blue one has a mass I don't know, and a velocity of 2,6. So I have here 2m times 1.5 equals mv plus 2,6m. Okay, 3m equals mv plus 2,6m. I can divide with m right through. Then I have 3 equals v plus 2,6. 0,4 is v. As a positive value, so it's moving in that direction. So the velocity is 0,4 meters per second. I'm just gonna look, they told me right, to the right, so I'm gonna use the same direction. To the, oops, right. Right. Another very important thing is sometimes, even though you're using all the equations correctly, something feels halfway through it's not working out. So when you saw that you weren't given the masses of these objects, then you might have panicked. Okay, all you need to do is just continue out with the equation, continue with the equation. The equation is going to solve itself. Because the masses are the same, I could have just made them X if I wanted to, but I just made them M for mass. The M's did cancel. So it was not applicable. Cool. Okay, I'm going to stop the lesson. I just want to show you something. Your screen might be blurred quickly or whatever. I'm just going to show you something. I just want to get a new share here going. New share. I think it's this one. Is the page now looking different? Speak to me. Good, sir.
Yes.
Okay, this is the YouTube channel. You just type in, it's Afrikaans, you type in Wiskunde Skynat on YouTube. You'll get here. And then you can go, I don't know, playlists. I don't know if you can see where playlist is here somewhere. And then you're going to look for physical science. There we go. Grade 12 physical science. You can click on there and there will be some videos there. Okay, there's a video still processing for you. But basically all your videos will be under physical science, or your grade 12 stuff will be under physical science, grade 12. So I'm loading last week's video. I'm loading today's video as well. Okay, so this is just like a data bank for you to go back to if you want to. All right.
Okay.
Right. I need you to do the following. I need you to do all the work on impulse momentum in your textbook. Also, I need you to do all the stuff on law of conservation of motion. Okay. There will be a small section that we haven't done yet. It's going to be about kinetic energy. So they're going to ask you, is this collision, is it elastic or not? That's a small part. We can discuss it next week, basically. So you can have questions on that. I'll just discuss the questions. This is a small section. And basically, you need to work out the kinetic energy before the collision and kinetic energy after the collision, which is really easy. Just to find out if something is elastic or not. Right. There's a very
Okay.
We're not finished with this chapter. Next, we're going to connect again. We need to speak. We need to if you're gonna have a problem connecting on Fridays at this time, then you need to start chatting to me on alternative times. Okay. So Reese, are you guys gonna have a problem connecting Friday afternoons?
At 11:30, yes.
Okay. Right. Can't we just make just get a time for next week, basically? So that
Kutsal will be available anytime from Monday to Thursday between 7:30 and 1 o'clock.
okay. I am not available on Wednesdays. I'm not available Tuesdays and Thursdays till 11. So I can see you guys on a Thursday or a Monday or a Tuesday at 11.
Anyone will be fine with us.
Why don't we do Thursdays 11? It just gives you that extra couple of days to finish all this work. I mean, I can tell you, okay, let's see one another Monday at 11, but you're not going to be ready because you've got lots of homework. So let's just change. Next week is the 18th. Let's just connect at 11 to 12, between 11 and 12. And in other words, what time is that exactly, Reese? 5 minutes to 11. Ah. So 5 minutes to 11, we're all on it already. So 5 minutes to 11 on Thursday, the 18th, we're all online. And then we just get a feeling for that time. That might be a nice time to keep as a constant or a time, a permanent time. If that's going to work, Reese.
I'm sorry, Charles. We currently don't know. We first need to check what the other grade webinar times are, because the problem is they're doing the webinars the same time we're doing the lesson, and that puts strain on the internet, obviously. So we just first need to ask Diana and see when they aren't doing webinars.
Okay. So take a note of the following. I can either see you, let's make the following times. You need to choose either, I can actually do Wednesday morning, either Wednesday.
Charles?
Yes?
Charles? Hi, it's Cedric here.
Hi, Cedric.
Can I contact you and we can chat about times?
Yeah, but can we just finish off that today? Because I've also got other people that I need to actually take in consideration. If that's possible.
Okay,
Hello?
I'll have to chat to you on WhatsApp. Sorry about that.
Okay, but can we just fix a tentative time for next week as Thursday 11 to 12? Just so that there's a time in the bank. And then you're going to get back to me if that's working for you or not. Okay. But you're going to get
good, thanks.
Thank you very much. Well, Liesel, bly net gou aan.
Is reg?
Okay, Reese, keep well. We'll sort out
thank
a
you.
time. We'll sort out a time. It's not a problem.
Okay.
Bye.
Thank you.
Bye-bye. Okay, Liesel, kan jy my gou hoor?
Ek hoor jou, ja.
Ek hou donderdag die 18de die tyd vir jou 11 tot 12 uur. Whatever, hulle gaan lank vat om te besluit. So moenie bother oor hulle nie. Al moet ek nou volgende week op 2 maniere klas gee vir daai week. Ek en jy hou daai tyd 11 tot 12 uur. Tensy hulle saamstem of iets is dit. Dat ek jou net kan, jy weet, ek kan nie van mense rond te neek wat tye betref nie. Pas daai tyd jou beter as Vrydag in elk geval.
Ja, hy pas ons definitief baie beter. Okay. Maar ons is baie fleksibel tussen Maandag en Donderdag. Ek meen as jy vir my enige tyd gee, tussen 8 en 1 maak ek dit werk.
Okay. Alright. Okay, cool. Ek gaan julle laat weet wat hulle sê.
Okay.
That's it.
100%. Baie dankie, Charles.
Hy moet sy werk doen. En ek dink hy doen.
Ja, nee, hy is 'n baie plusgetroue seun.
Okay. Ek het baie ander werk vir hom. In die vorm van vraestelle. As hy enigiets soek, daar's ontsettend baie werk beskikbaar vir hom. Voorbeelde met ander woorde. daai handboek se voorbeeld kan dalk baie keer 'n klein bietjie min wees.
Ja.
So, no problem, ek kan baie vir hom kry.
Baie dankie. Ja, jy kan vir my aanstuur, ek sal vir hom print.
Okay, ek gaan vergeet.
Ek sal jou 'n boodskap
Ja,
stuur.
hy kan ook maar my nommer vat en moet my so nou en dan sê, okay, hy soek nog iets of iets is dit en dan sal ek vir hom deurgee.
100%.
Okay,
Baie dankie.
plesier. Goed gaan. Bye bye.
Goed gaan. Bye.